Okay, welcome everybody back to another session of EL 164 Online. Today we're going to talk about Chapter 15, Part 1. This is the section where we really start breaking more into the the compact logics. We're breaking right into that, learning more about how that unit operates and addressing it and all these fun things we're going to be doing here. So without any further ado, I'm going to break right into it. So here we are, the ControlLogix controllers, Part 1, Memory and Project Organization. Starting with memory layout. So here we're looking at some different pictures of what the ControlLogix platform looks like. A little bit different than the SLIC 500 that we've seen in previous chapters, but the principle's still there. You can see they have both. Here in the pictures here, they show modular styles. They actually have a fixed style. The fixed style is the one that we are actually using, is the L16ER, which is not illustrated here. One of the points that they're bringing up here is that there is no fixed areas of memory. In the SLIC 500, they went out and defined areas of memory for bits and words and that sort of thing. Here in this software, you get to define all that yourself, which makes it that much more user-friendly. Configuration. So again, the modular, here they're showing the modular ControlLogix system. They have essentially a program that operates what they call asynchronously. It uses, goes out, it reads the inputs and outputs. At the same time, it updates the PLC. At the same time, it's sending out the communications and all that sort of thing. One of the points they're also noting here is that they still use the RSLinx. I didn't get into too much detail on this, but this is the RSLinx is a software that the Allen Bradley has developed to set up communications with PLCs to laptops and computers and whatnot. This RSLinx still runs in the background with the 5000 series software. It's just not as prevalent as it is in the RS500, whereas 500 you'd have to open up RSLinx to get any communications going. Here in RSLinx, they give you a lot of those tools right in the software, so you're not having to open up second software. Still, on occasion, you'll still end up in a situation where you may have to create a driver to talk to a new PLC that you haven't talked to before, and that's where RSLinx would come into play as another software package. Here they're going into some of the properties. We've kind of went through that. This is the last lab there. We developed the hardware configuration, so we're going to be going through a little bit of that as well, and showing us some of the controller properties, how we go about setting up those properties here. So again, we type in the manufacturer, the part number of the unit, and then we give it a description. And this particular one that we're using as an example is a 7-slot chassis, so it is a modular style, whereas the one we did in lab, of course, was the L16ER, excuse me, and that unit is a fixed unit, so we don't have the 7 slots. It's just got the fixed I/O associated with it. So, and here they're noting that the processor resides in slot 1. One of the things with the 5000 software is that processor does not have to reside in slot 1. They can move that processor around. They can also have more than one power supply. So they can put, if they have a lot going on in the rack, like high-speed counter modules and servo modules, that sort of thing, that take a lot of power to operate, you can put more power supplies on the rack to feed the backplane to give you plenty of power to operate all these type of options. So again, like that last slide, we kind of went through some of this, and we're going through it in the lecture now, is the I/O configuration. So this is a part of that tree that we looked at in that lab. So we're looking at I/O configuration here. So this is the very bottom piece of that. And it is in that selection we find this module's properties. And here we've, of course, got the name, description, the input data means it's an input module, and the revision number. So we saw on that last one. This particular one looks like it's at slot 0, which I don't think it can reside there, but I could be mistaken. Project. Okay, so here's the project. We're looking at controller tags. We've got I/O data, system shared data. And then we've got the task of main routine. You can have other routines, like say you have subroutine 1, 2, 3, 4, or if you wanted multiple subroutines. We'll be discussing that in lab as well, going through how to develop some subroutines. And program tags, local data associated with the program, so any tags that we generate or create are going to be a part of that. So again, this is kind of the organizer. If we look at how we did this in lab again, we've got the RSLogix, controller tags, tasks, periodic. This would be where the main routine would reside, and then we got some data types at the bottom here. So tasks, this is something that we're not really going to get too much involved with in this class. It's more of an advanced type solution, but the idea is that you can have a routine that runs continuous, like you would typically have. Most of your programs are going to be in a continuous task. So every time this PLC scans, it runs all of the different programs or sub-road programs that you have available. You can set it up so that there's a periodic task, so it only runs those tasks when requested. As you can see here, the continuous task, it starts with program 1 and goes right on down, and then again returns to the top and starts at the top. So if we had, say in this particular case of this example, they've got they're showing us 32 different programs, so we can continuously scan. From 1 to 32, goes back to the top, starts over again. It doesn't have to wait for the inputs, doesn't have to wait to update the outputs, doesn't have to wait for any of that. It is a continuous process. So it's a process that stands alone, and remembering that term asynchronous. So they asynchronously operate the scan of the program, the scan of the inputs, and the update of the outputs all at the same time. So they're going to talk about periodic, where you can set up a time base or interrupt or something of that nature. I'm not going to get really too involved with it because most of the time you're not going to be using any of these tasks. So I'm just going to make you aware of it, that you can make it so each one of these programs are called at a different time. You can also have them set up as an event, so when some input takes place, it triggers that subroutine to take place. So programs are considered the second level of scheduling within a project. So here we're looking at, they kind of put it in order in a fashion such that what has to take place when. So as you can see here, you've got the main task. It's going to run the main program, then it's going to run program A, that's going to run program B. So that's kind of what they're referring to there. As you can see here, the main program is scheduled to execute first. Okay. Routines. Okay, so are considered the third level of scheduling within a project. Here we are. We're looking at each routine contains a set of logic elements for specific programming language. So in this particular case, we've got ladder. And any one routine must be completed in the same language. So you can't start a routine in like text and switch it to ladder. It's got to be in the same format. instruction. So structured text here, sequential flow chart. We talked about these a little bit last class. So we got sequential function chart, structured text, ladder logic, and function blocks. We're going to focus solely on ladder logic. I mentioned before, the structured text is getting pretty popular with the younger generation coming into this industry. I started seeing more and more of that toward the end of my working in this field on a daily basis. But nowadays, I think we're going to still see a lot of the ladder logic, and then eventually we'll see more and more structured text as young people prefer to use a structured text over the ladder. So kind of a recap, the main routine is execute first, then the subroutine, and then the fault routine executes it afterwards. Tags, we did go through this a little bit. I'm going to go through this again here, how tags are developed and what their meanings are and whatnot. So here we've got a tag name of like local, that means the processor is local to us. :2 means we're looking at slot 2. Output means we're looking at an output. And data means that's the location where this information is going to be utilized. So in this particular case, this is an output, so we write to this location, or we turn on a bit in this location using the ladder logic, and then that PLC sees that address go high, and when it reaches that output card, it turns that output on. So it's going out there and scanning those outputs asynchronously, not at the same time that the program's updating them. So it's doing it at the same, they're both operating at the same time. So when it gets to this data table, it sees this bit on, it turns on that output in that output card. So see here, we got just kind of an update on the tags here. So when the program operates, it's reading and writing information to these tags, and these tags are going to memory locations. So like if it was an input or an output kind of thing, it sends that information to the proper data table, and then the PLC takes that information and reads inputs or updates outputs associated with those data tags. So a program scope tag. Now again, we had this. This was mentioned before in a previous class. We had program scope tags. These are the tags that we want to use. These are the ones that are consistent of data that can be accessed by routines. I'm sorry. These are the ones that are specific to a program. These are not the ones that we necessarily want to use. It's the controller tags that we want to use. These are the ones that are the controller tags are the ones that are used throughout the entire program. These program scope tags are specific to one subroutine. So we want to make sure that we're focused on the global data, not the local data. Everything we're going to be doing is going to be in the global data. So when you make the mistake of creating tags in the local data, what happens is that subroutine doesn't necessarily go out and look at other subroutines' information, or it doesn't necessarily update those tags. And so when you have tags in this program scope location, it doesn't update those tags, and so you're missing information every time you scan the program. So here we are, we're looking at a couple different programs here shown within a project, identical names, tags. So as you can see, if you have a program scope tag, you can write that tag specific to a subroutine, and you can duplicate that because they are written specific to a subroutine. This tag can match this tag. Otherwise, if you're in a global sense, you wouldn't be able to, because it would be looking at that same tag in both subroutines. So here we're talking controller tags. This is the location where I really, this is where we're going to be spending all of our time creating tags. Here is under program tags. This is the area where we get into a little bit of trouble if we write tags there. It doesn't necessarily get read across to all the subroutines. So we focus mostly on creating tags in this location. All right, so here's some more information about the data tag type. Defines some basic operations. So again, here we have local, which of course means local to the PLC. The 2 represents the slot location. The O represents an output. Data represents the information that we're going to utilize, and 4 represents the bit that we're actually using in that application. And here's a breakdown of the whole thing here. Location is local. Slot, number of, so in a fixed application, that slot was what number? It was a 1. Because that's what the processor defined as being their slot. It was a fixed number of I/O, so we'll just define it as 1. Okay, next piece is type. So input, output, configuration, or status. As you remember when we were online, you saw I/O and a C, and then there's also an S that we didn't really get too involved with. Member, submember, and bit. Typically, most cases, like the optional is submember. You get into that mostly when you get into more complicated cards like analog cards or high-speed counter cards or something like that. They break down a submember of the you might have a channel 1, channel 2 type thing of an input or something like that. So member is of course we're going to have type is going to be an output. Then we're going to have a member say let's see here. Member is going to specify the data that the module can store. So we're talking either data or a channel number or something of that nature. And then the submembers are going to represent the number that's like say if we had a channel 1, it'd be CH, and then this would be channel 1. So that's how they tie that up. And then the bit specific to the digital I/O module, so whichever bit we're using. So, and here's kind of how it breaks down again. So we're looking at the data table, and they're showing us a bit 4 being active here. So local, slot 2, output, data, bit 4. In the 5000 program, you're able to use what they call an alias tag to attach to a base tag. So as you can see here, you've got a controller memory of local to output data 5, this was bit 5 of the output slot 2. As you can see is the base tag, and you can assign a alias tag to that. In this particular case, he used fan motor as an example. And here is a simulation on how that can be done. Just like that. Produce consume tags. These tags are used to share information between processors, between PLCs, so you can share information with 2 PLCs, excuse me. The produced, of course, is just as it sounds. Produced is the tag that's actually being transmitted from the source PLC, and consumed is the information coming from the PLC. So they got an illustration here of how the consume tags are going into the PLC, and the produce tags are coming out of the PLCs. We'll get a chance to play around with that a little bit in lab. So you can set up your system to configure your applications for both global and other controllers to consume, so you can set it up so you can talk to it. You got to set up the configurations and whatnot. We're not going to get too much involved with that, but I'll at least show you the process of creating, consumed, and produce tags. But here you got to get into more of the networking aspect of things. This is where learning networking, and I think I mentioned before, where the two worlds of computer and CIS type level, where you've got your computer geeks and all those guys over here, and your PLC people like us that will be kind of bonded together in a situation where networking is that bond that ties us two together. And you'll find in the future that more and more of that separation between CIS and PLCs is becoming more closer linked to one. Here's some of the different data types. As you can see here, we got Boolean, single integer, which is 8 bits, integer, which is 16 bits, and then double integer and real are both 32. One of the things that we do know from the operations of the ControlLogix platform is that it is a 32-bit based operation. Notice how even the Boolean here, let me pull up the laser pointer, the Boolean, even though you may only assign 1 bit to Boolean, notice how it actually utilizes an entire 32-bit word. So it may only be operating off 1 bit, but it's actually using 32 bits. The same thing with this guy down here. We are using 8 bits, but it's still a 32-bit word. Again, the same thing with integer. Here we're using 16 bits, and it is a 32-bit word that's actually being utilized. So it's using up all 16 or 32 bits, excuse me. So quite honestly, the best solution always is to stick with a 32-bit word, a double integer in the ControlLogix format, just simply because it is a 32-bit word. Even in Boolean, you'll see if you, and we'll go into that a little bit in lab, where if you put a 1 in the string length of Boolean, it comes back with 32 bits. So we'll be getting into that in lab. So a Boolean is, again, is 0 or 1, and you got other bits 0 to 31. Single integer is 8 bits. Integer is 16 bits. Double integer is 32 bits, and then the real world is 32 bits as well. The structures, here we are. We got structure type tags, grouping of different data types that function as a single unit and serve as a specific purpose. Okay, so here we're looking at, like for instance, this looks like a counter, I think. Timer timing, timer enable, done bit, overflow. It could be a timer, I suppose. Preset, but these are just different data types, even inside a timer counter format. So, and we'll be getting into that more in the future. So here we are saying there's a few different structures available. Again, double integer, Boolean, 2 different pieces. So double integer, of course, that's a word, and this is going to be individual bits. And this is more of a counter application, and we'll be getting, like I said, we'll get into that more in the future here. Module defined bits, again, when we actually bring in that, open up that software for the ControlLogix L16ER, we notice how it automatically populates the inputs and outputs for us, because what? It's a fixed I/O unit, so it already knows how many inputs and outputs that it has, so we don't have any additional configuration associated with it like we would here, where we have a modular solution where they've got to incorporate individual slots for each input and output. And then they got user defined. So here we are developing some of our own tags. We did that in the last lab. We'll be doing a little more of that in the next lab. Okay, so here we're looking at editor tags. Again, we want to make sure we're in what? Controller tags, not program tags. Controller tags is where they are globally available. Program tags are only available to each individual subroutine. So make sure we're getting that correct. And we'll be getting into subroutines in lab a little bit to explain those a little better. So I'll continue on here. So again, defining tags, we kind of did this a little bit. So we cannot use what? They are going to be names can contain alphabetic characters, numeric characters, and underscores. But they must begin with an alphabetical character or an underscore. And let's see here, and may only be up to 40 characters long. So, which seems like a lot, but sometimes when you get into some really technical applications, they may be a little bit, have to be shortened a little bit to get all those characters in there, but pretty good solution. So here's the different types of tags. Tag types available: base, alias, produce, consume. When we get into the produce and consume, that's what we see in that piece of the puzzle there. And most everything we'll be doing is out of the base anyways. Data type, again, we kind of did that a little bit in last lab, but the Boolean, integer, double integer, single integer, that kind of thing. And then the scope, we're going to stick with the scope of the program itself. We can display the style, binary, octal, decimal, hex, and we can change that at any time during the operation. So here we are to create a tag in the new tag dialog box. Again, we're just going through the process. We enter the name, a description that we like to put in there for that tag. Base, Boolean is going to be an individual bit. Base means it's going to be based on the tag itself. There's not going to be an aliases or a produce consume attachment. And the style is going to be shown in binary, so it's going to be in a 1 or a 0 format. Monitoring and editing tags. So here we are. We'll be going in the lab a little more in depth on that as well. So here we're going to actually go into the actual value or the look at some of the more details of those tags. Knowing how it's laid out to the scope is the controller. We're going to be showing them all in the base tag. So we're sorted by base tag, and then we display the information as same. So we go down to edit tags window here. We can actually get in here. We can start modifying these tags. And arrays, I just want to make you aware of them. We're not really going to get too in depth on those in this class. They can get really complicated, really easy. But if you think of it in the section, the consideration of one-dimensional is what we're going to be mostly focused on. Is just by creating one tag and then taking that same tag and creating like 10 tags of that same thing, something like that. You can go two-dimensional where you create one tag with 3 different words to it, and then you could have individual bits per tag, and then you can continue. It just keeps getting more and more complicated as you get more into it, but we're going to focus on the one-dimensional. So here we are. You got the ability to adjust the dimensions here. We usually only are going to mess around with dim 0, where that gives us that one dimension. That's all we're looking for. Okay, then this last piece is the single dimension shown here. So if we entered the value of temp 0, an array of 5, it'd give you the temp 0 through 4. So that is the end of part 1 of chapter 15. I'll be moving on to part 2, chapter 15 here next. Thank you for your time.